welcome to the session. And today we are going to first have a keynote, and we're honored to have our keynote speaker, Dr. Camenisch. Yan is the VP of Research and Crypto at Definity and the director of the Definity Zurich Research Lab. Before that, Yan was at IBM Research Zurich for many years and was leading the privacy and cryptography research team there. So Yan is a leading researcher in the area of privacy and cryptography, and he is an IACR fellow, IEEE fellow, and ACM fellow. And he has published over 140 widely cited papers and has received the ACM SIGSAC Outstanding Innovation Award, IEEE Computer Society Technical Achievement Award, and IFIP Christine Beckman Award. So today, Yan will talk about the applications of zero-knowledge proof to the design and the construction of cryptographic protocols. So the talk will be roughly around 45 minutes and followed by 5 to 10 minutes of Q&A. And Yan, I will give you like heads up before 2 minutes before the end. Okay. So without further ado, let's welcome Yan.
Thank you very much. So I guess I'm going to share my screen. If that should work. And welcome everybody. Takes a while. Share my screen. Good. So today I would like to talk about zero-knowledge protocol, obviously, given the focus of the conference. But my focus will be on zero-knowledge protocol in the context of constructing cryptographic protocols. And so, like, indeed, like cryptography, this was the stress on the graphy part is really a constructive science. So it's about building stuff, it's about building encryption schemes, but also, and what I care about is really about building protocols. So in some sense, it's like, you know, like an architecture, like a builder. It's a bit of a science, but it's also a bit of like an art. And so I think it's fitting very well. So, you know, when we think about how to build a protocol, maybe we think about the construction business. Okay, well, let's build a nice cottage at the beach. So that's our goal here. But actually, I think in crypto, quite often it's a little bit different, because actually we end up doing something like this. We have our cottage in mind to be at the sandy beach, but actually then we end up deploying it in a quite different environment. And so that's like the tricky part here. And actually why I chose the moon here is really, like, computers somehow are different than like our normal environment, right? Like the sandy beach or the paper-based world is sort of what we are used to deal with. But the moon is really different, right? And for one thing, is the footprints there are forever. So the footprints of the astronauts are still up there in the sand or in the dust. Whereas on the sandy beach, the beach will throw that away or like wash it away. And that's more how humans think. And sort of computers really store data forever. Data mining gets ever better, and that's very, very hard to deal about. My point is, sort of, we have to think more about when we do develop protocols. We really have to think about how, in which environment these things are used. And actually, we want to have it used in any environment, whether it's like on the environment we're used to on the moon, but maybe even on much nastier environments such as like Venus. Okay, so let us think about actually what is the process about building cryptographic protocols before coming back more towards zero-knowledge proofs. And so here's sort of something that we actually, or some of us, I hope, are doing most of the time when constructing a cryptographic protocol or designing it. We first have something like a very abstract view in mind. Okay, we want to have some shelter where maybe it can enter. So there's a door here. Maybe it should have windows as well, so we can check what's on the outside before actually we leave our shelter. So we have to have some abstract, or actually finding the right abstraction. Then we want to do the next level, actually try to design a protocol that satisfies that. And quite often we think about that, okay, so there's some building blocks, signature schemes, encryption schemes, and so on. And then eventually we want to deploy it in the real world. So we have like a real version of the cartridge that we built. And that looks quite different from the one that we had in mind. Nevertheless, you want to make sure that the features, it gives us shelter, it has windows, we can like look outside, and it has a door we can enter and leave. These features really be maintained, be guaranteed in the real version. So we want to have like security proofs between all of those steps. And of course, if you care about something in practice, then actually you want to also read a protocol like efficient, so actually can use it. And this is actually it's not so easy to do all of this. And so it's really want to sort of look at both sides for how we use ZeroKnowledge Protocol actually in this whole process, but also in particular how we can use ZeroKnowledge protocols in actually building real protocols. And really, so I guess on one hand, some of that is maybe you could think about formal systems, framework for doing security proofs. But again, I think cryptography or cryptographic primitives are really one main ingredient here to this like spacefaring adventure. And as I said, today I want to look into like ZeroKnowledge proof protocols. And so I want to structure this in like 3 parts. So the first part is about like the practical aspects, how we can, what things are done today. And then I want to move more towards like theoretical aspects about this process, how we can make sure that protocols we design are actually secure when used in practice or actually in any environment. Let's start first with the practical aspect. So how ZeroKnowledge proof proofs and building blocks relate. There's a lot of like well-known and really well-defined primitives that we use today in cryptographics or in constructing cryptographic protocols, like signature schemes, encryption schemes, commitment schemes, verifiable serial random, etc., etc. So there's a whole bunch here. These primitives, we understand them well for most purposes, at least. Yeah, and we have like an efficient instantiation of all of them. Now, if you construct a higher level protocol, then of course you want to combine them such that actually work together, because maybe you want to prove something what you have signed, or you want to prove something what you have encrypted. And that's where cryptographic or ZeroKnowledge proofs come in. That's sort of the mortar that actually puts these things together, makes them hold together, that they actually can construct a nice house out of these. Actually, in theory, that all already works. I mean, we have good definitions of ZeroKnowledge proof protocols of all the primitives, and since we know we can prove anything in ZeroKnowledge, well, we're essentially done, right? Now, if we care about practical protocols, it's not so easy. There are many more things to come in. Actually, these things have to fit together. So let's look into that, and for that purpose, I want to use my favorite example protocol, which is like privacy protecting authentication. So here we have some users, we have some issuers here that maybe the government that issue credentials to the user, and then we have some third parties like a movie provider that relies on credentials that the government have issued to the user, for instance, to make sure that when Alice here wants to watch Alice in Wonderland, that the movie provider here can ensure that Alice actually is of age, or Alice in Wonderland is like 12 years old, so that Alice is actually 12 years old. But of course, the users want to be sure that here privacy be preserved, and so that not all the details get collected by the movie here. And so, I mean, as the picture somehow already suggests here, the building blocks could be like commitment schemes. So Alice could commit to her secret in some of kind of a public version here, public key version, send that to the authorities. The authorities would then sign the various attributes that Alice has on this public key here, produce a signature. And then Alice later on wants to go to the and watch a movie online. Then she could use ZeroKnowledge proof to produce a proof that of the statement that, okay, I got a signature from the government on some committed secret key, and that signature also attributes that I'm older than 12 years of age. So that's sort of my example protocol here. So how could we use that? Okay, so now, as I was saying, in principle, we know that these things exist, so we could go and build it. But if you would do this with generic building blocks, it would not be very efficient. So now we want to make sure that these things are efficient. And to this end, let's first look at zero-knowledge proofs and then try to find signature schemes and commitment schemes that work well together. So the primary example of zero-knowledge proof maybe is the well-known Schnorr protocol. I'm sure you all have seen that before. So it's like a protocol between a prover and a verifier. The verifier has knowledge of some public parameters like y and g, and the prover has knowledge of some x, such that well, the prover claims that y equals g to this x. So this is really a protocol that allows the prover to prove knowledge of this discrete log here. Now the protocol works as follows. The prover first randomizes or computes a random value, sends this, raises the generated g to that random value, sends it over to the verifier. The verifier receives that, chooses a random challenge, sends it back to the prover. Prover computes an answer here, like an S value, sends it back to the verifier. And now the verifier would accept the protocol if this relation down here holds. So that's the well-known Schnorr protocol. And it has the properties that we care about. First of all, it's a proof of knowledge of like secret values, such that actually meaning if a prover, if a party is successful in running this protocol, we can actually extract the value x such that y equals g to the x. And so that sort of gives rise to the notation here that I typically use, which is like a proof of knowledge of some value x such that y equals g to the x, where the red stuff being the secrets being proved. The other property we care about is, of course, zero knowledge, meaning that the verifier here engaging with the prover in this protocol does not learn anything from that interaction, other that it would be possible to extract such value from the prover by running the protocol. Another nice protocol, nice feature of this protocol is that it can be made non-interactive, as you all know, by applying the Fiore heuristic. Essentially, instead of computing the C at random, just hash it given the T value and like some other context values such as y and g, maybe some message m, and derive C as the hash of that. And then we can make the protocol interactive, and we would denote that maybe there's a signature proof of knowledge of a value x such that y equals g to the x. Because there's two important observations here about this protocol. The first one is actually the protocol works for any group homomorphism from a group G1 to another group G or G2. And the other thing is that the prover and the verifier have work equivalent to one evaluation of this group homomorphism. So essentially, the prover has to do one evaluation here on the random value, and the verifier, on the other hand, has to do another evaluation. So it's a very efficient protocol because it's really one evaluation of this homomorphism. And here's a couple of examples for which this the Schnorr protocol works, or really just examples of group homomorphisms. So of course, the classical example that we just looked at, discrete logs, where you take some generator and raise it to the power of x. It could actually be two secrets, and then you do sort of a representation proof here. So we would prove that, you know, U and V such that they give raise to G to the U to H to the V. But that also works, or actually a whole tuple, that also is a group homomorphism when you map inputs to a tuple of output elements. So that all works. It's very generic, as you can see. Nice enough, also it works for bilinear maps, because that just also defines a group homomorphism. So like the expression here is a group homomorphism. So E is the bilinear map, G are two generators. So that works nicely. Actually, also if you have two input elements, you can also have those appear in one of the arguments to the bilinear map. Or actually even this one is a group homomorphism where you sort of take an element in G1. And so it's not an exponent here, but it's actually the group element. So that's also a group homomorphism, and the Schnorr protocol just works very nicely like that. However, what wouldn't work is we cannot have like a multiplication of two secrets in the exponent here. So we would have to do a workaround around that. But, like this, it wouldn't work. Also here, if we have u and v as exponents in two input elements to the bilinear map, so that wouldn't work. For this case, where again you have like the one of the group elements here as a secret or the exponent as a secret. So these are statements that do not work. However, we could combine homomorphism with like and or statements. So statements like this would be valid, or like an or statement like this would be valid as well. And I guess as we are on the ZKProof conference, would just like want to point out that actually these things could be standardized, so it's very well understood, and we could just standardize those things as a very nice building block to construct protocols. Well, I guess I'm sort of making a bold statement here in this. Well, I guess it's true, but in the sense that okay, I've just given you one building block, but then actually we want to have one much more, right? We want to have signature scheme, encryption schemes, commitment schemes, and so forth. And then actually we would have to use schemes that are compatible with the language we just defined, right? So we want to have a signature scheme such that the statement, like I know a signature in the message, such that that signature is indeed a signature on a message on some public key, so that this statement here is true. So that would be the statement that we would want to prove. And now, of course, we want to have signature schemes such that this statement is actually in the language of the proof protocol we were looking at before. So let me give an example here. Oops, too fast. So we want to have a signature scheme such that this statement here is efficient. And there's a number of those signature schemes, but like maybe the latest one is by Poncheval and Saunders. And so it's a signature scheme in the bilinear map setting. So we have a bilinear map here. And then we have two secret keys from actually the group of the order of G1 here. And then sort of the public key of a signer would be a value capital X as G to the X and capital Y being G to the Y. That's the public key. A signature now here is defined as a tuple A and B such that the equation here holds. And A would be a random element that B is computed from A is this equation over here. And so I guess you can verify yourself easily that if you compute that like this, actually this equation would hold. So a signature is valid if this statement holds. So now, actually, let's think about it. So if now I want to prove knowledge of a signature on the message of the signature, so M, A, and B would be the secret values. And I would want to, oops, I would want to prove that this statement here is true. Now, unfortunately, this is not a valid statement because now in this part here, I'm mixing group element and exponents. I was just saying before, that's not a valid statement. So we have to deal with this. This part actually would work out well. So I could have that. So if there was no M here, it would be valid. If there was no A here, it would also be a valid statement. But like this, it's not valid. So what can we do about that? Well, let's look at that. So we have to get rid of maybe this or that part. So one trick is, okay, well, just instead of maybe providing or like proving that we know A, maybe we can just provide an encryption of A under some, let's say H would be a public key, or actually just two random elements, G and H. So we can do an encryption of little a here to get like a tuple. And now if we do some reformulation of the equations of the equation here, we can actually see that if we were providing these values, then we could prove this statement down here. That would be a statement that we could prove, showing that actually we do know a valid signature. Now, if you look at that, so this part is valid. This part, well, actually, it's not valid because we have a multiplication here, and this part is valid. Now, the question is, okay, so what can we do with the multiplication? Well, we could also say we proved that we know some value U, such that actually that value U is the product of two other secrets. And if we do that, we can add some other. So we get this equation here, we just replace U by, or like R times M by another secret, say, call it U, and then prove that U actually is equal to R and M, which these two terms here do, the terms involving A prime. Okay, so now actually we have a statement that we can prove that we know a signature on a value M by running this proof protocol here. So now we have achieved our goal. We have an efficient signature scheme that, for which we can efficiently prove that we know a value, a signature on a secret message. So that's how we want to construct proof protocols. And this is really just one example. Right? There's a whole bunch of primitives here. We have a number of signature schemes that work. We have a number of encryption schemes that would work here, and then we have a number of commitment schemes that would work exactly along those lines, what I've done, I've just shown you. So we actually, with this generalized Schnorr protocols, we actually have a full framework to construct cryptographic protocols that are efficient, that are secure. But actually, there's a couple of other frameworks along the same line. So that just gave you some hints of the Schnorr proof, discrete log-based primitive framework. So I guess this one is well understood. There's lots of primitives. I think that these are the most efficient solution. The only drawback is that actually, if you want to have non-interactive proofs, then you have to believe in the Fiat-Shamir heuristic. So if you want to have strict probability, there's a bit of a drawback here. But I guess for practical purposes, that is probably quite well. Now, then the next framework is gross-to-high proofs together with structure preserving primitives. So these gross-to-high proofs, they are non-interactive proofs which do not rely on some heuristics. So if you don't want to resort to Fiat-Shamir heuristic, you would go to use gross-to-high proofs and some structure preserving primitives. I think these are also very well understood. There's a fair amount of primitives. However, requires pairing, so it's less efficient. But also the proofs are actually rather short. So sometimes in the Schnorr-based protocols, the proof could get somewhat lengthy, but actually with gross-to-high proofs can typically be very short, even something like 3 group elements. However, here the security of many primitives rely on the generic group model. There's even a third and a fourth class. The third class is like Starks, Snarks, bulletproofs, etc., and together with algebraic circuits. And now people also work on primitives that are actually nice together with this algebraic circuits that are actually targeted towards this Snarks and Starks. So I guess these are also very expressive in terms of the statements. Some of them give also very short proofs. I think in this area is still a lot in progress and still more primitives that we want to look out for, that we want to design. And even in some sense more cutting edge research, or I guess by the same cutting edge, but still a lot of work in progress, but even much harder, I guess, to achieve results is like the lattice-based proofs and some primitives. Like if you care about post-quantum security, then you have to go towards other primitives. Here is still a lot of stuff ongoing. Some require also the Fiat-Shamir heuristic because they apply the generalized Schnorr proofs on like lattice-based primitives. Because at the bottom line is there's some well-understood things that we could actually standardize now and move into practice. Like up here, whereas down here, like more work is needed. Okay, so this sort of concludes my first part. That was about how can we construct cryptographic protocols from zero-knowledge proofs and primitives. The message being there's a lot of stuff out there already that we can actually use as construction frameworks. Now let's go to the second part, more towards the theoretical aspect. And so this one is about how when we prove security about our primitives. Actually, it's not so easy as it seems, in particular if you want to use the UC framework. So here we are. So that's what we want to do, right? We want to like specify our ideal functionality. Then we want to do some hybrid protocols using known primitives, signature schemes, zero-knowledge proofs, commitment schemes, and so on. And then actually we want to instantiate all the primitives by their actually real instantiation and get the actual protocol. And the hope is that we do this, we define the ideal functionality, prove that the hybrid protocol satisfies that, and then assuming that that each of the primitives are secure, then actually the framework would provide you the security proof here so that you do not have to do this step. And actually what is nice about the UC framework is sort of actually guarantees that it is applicable in any environment. So you do not have to look at how your protocol is used in connection with other protocol, but actually it just works because it's like composable. Now, okay, so as I said, the first step typically is you define some ideal functionality to a hybrid protocol. Then this hybrid protocol you build from like other ideal functionalities. Then you instantiate or prove that actually these functionalities, this intermediate primitive schemes functionalities are implementable. Proof that, for instance, now here's a signature scheme functionality that this actually is satisfied by, I don't know, like an RSA signature scheme. And then from that, the framework would make sure that actually your house is good. So that means you would have to do these two things like every time you want to build a protocol, define your ideal functionality, define your protocol, and then prove that your protocol implements the ideal functionality. But all the rest should sort of be done for you, right? I mean, you want to have the library of secure primitives, and the framework then proves you this thing. Now, right, because that's what I just said. So really what we want to do is we sort of want to have like a modular construction framework with modular proofs, and with idealized functionalities, idealized primitives, and then use the whole power of the UC framework. Now, I guess, yeah, let's look how this really turns out in practice. We've used look at the UC protocol or UC framework. So here we are again with my favorite example, right? So you want to have like a signature scheme on a message, and then we want to prove that we have a signature on a message. So that's our protocol. And so now if I look at the protocol from like a UC perspective, well, first I would sort of define an ideal functionality. It sort of defines how this works. I would have to define how the issuer and the users work together. And then I would build an implementation that use my signature scheme and zero-knowledge proofs, right? So if I want to, so my protocol essentially is, okay, so first I send a message here, I get a signature on it, and then once I have the signature on the message, I would use the zero-knowledge functionality to produce a proof and then send this proof over here. So simple protocol, quite clear how that would work, right? And so I guess, yeah, so I would have to first do some ideal functionality for my credentials, right? So sort of get a credential protocol where the user inputs the message, the issuer is asked, do you want to sign this message? Says yes, and then the user would get the signature. The user would then have like an interface, like, I want to have a proof here, I have M and S, and the functionality would give a proof if that signature is a valid on M, or actually if it was signed here. And then on this end, either you could verify credentials to see whether a signature is valid on a message, or it could verify proof to see whether actually this proof is really a proof of some knowledge of a signature of a message. But spare you the details here, because we really want to focus on the high-level protocol. Okay, so now we want to realize that with using signatures and commitment schemes. Well, you would hope that you could say, well, okay, so now I have a signature scheme. So I just receive, as an issuer, receive the message from the user, call the F6 functionality to get a message, a signature on that message, and then send that signature to the user. So that's pretty straightforward. Then also, I would think that now, of course, S is verifiable by calling F signature, but so now in order to produce the proof, well, I can just define what we have the zero-knowledge functionality, define the relation as being the message is and signature is a valid message signature pair with respect to this public key of the issuer, put that in there, and then get an answer back, and I can send that back to the issuer, to the movie, for instance, to provide that I actually have a signature on a message. Now this doesn't really work And let's see why it doesn't work. So it actually doesn't work for a couple of reasons. So in order to figure that out, we first have to look at the signature functionality. The signature functionality is essentially this thing here. You can ask it to sign a message, you would get a signature back. Then you can also ask it to verify whether a signature is valid with respect to a message in the public key, and it will tell you yes or no. And so actually there's two versions here. One version is where the signature is sort of generated by an adversary. So the signature is really just any string that the adversary provides to the functionality. Later on, there's extensions here where the adversary just tells, gives the functionality to algorithms, so the functionality can generate the signature strings itself. So it doesn't have to ask the adversary every time it wants to assign a message. So that's how this thing works. The ZeroKnowledge functionality actually is parameterized by a relation. So you have to parameterize the relation, which is sort of nice for us because our relation would be, here is a public key, a message, a signature, and the relation is valid if that is a valid message signature pair with respect to the public key. But what it does is it takes as input sort of the public key, Y would be the public part and the witness. And in our case, the witness would be the message and the signature, and Y, the instance would be the public key, the sense is in. But then it tells the other party, the verifier, whether or not the statement is true. So actually, this one doesn't even produce a proof. So indeed, so there's a number of reasons why this we cannot use those definitions. And really, the first one, this is interactive, so I cannot generate a proof that I could send over. So I need to get a proof string somehow that I could send. So this we have to change. Now, I guess that's not so hard to do, actually. But what is harder is the relation R here would specify as it is only valid if this verify statement holds. It actually talks about an algorithm, but actually fsig here is agnostic to the algorithm. So if we have the in the one version where I have the adversary to produce the signature string, there's no algorithm whatsoever in fsig. So this just, however the adversary cooked up as is up to the adversary. There's no way that you can produce like a relation that has some algorithm in it, because it totally depends on the algorithm, what the adversary does. And even if we had the other version where the adversary actually provides the algorithm, we still, in our protocol, we have no control over the relation here, right? Because in fsig, the adversary provides the algorithm. If you just use it in a hybrid protocol, we have no clue what this algorithm is, and therefore we cannot use ZeroKnowledge, because here we have to specify the algorithm. But actually, much harder, even if we sort of have figured that out. If here in the relation we talk about an algorithm the result of an algorithm being 1, actually here it's not whether this verify here is true. It's actually not defined by an algorithm, but actually you have to go and ask the functionality. There's really 3 ways that this doesn't work. Now the first one, the ZeroKnowledge being interactive, we can fix that. So there's like a definition by Groth et al., which actually they use for the ZeroKnowledge proofs, where they output a proof string. So that actually could work. We could just use that definition. But now, of course, the relation R talks about specific algorithms. So that means we would have to parameterize fsig also with algorithms. But also we can just not allow the adversary to input the algorithms, but just allow the adversary to define the public keys and secret keys of the signer. And there's some new definitions of fsig that actually would work with that as well. So that is solved. But actually the last part here, still the statement that verify here equals to 1 does not imply that fsig would actually answer with 1. Now, of course, for any reasonable implementation of a signature scheme, that's actually what is guaranteed. So, but that is not obvious from fsig. So we would actually have to look into into how fsig is realized, and then prove that actually for any realization of fsig, this would be true, right? So it's not something that would fall out of the UC framework, but it's actually something that you have to analyze on top of that. So this doesn't really work, right? Because if it would be a hybrid protocol, then fsig and ZeroKnowledge would have to talk to each other. And so, and that again doesn't work in the UC framework. So let's look at that. So actually, coming to the third part here, how can we actually do modular zero knowledge protocols in like the UC framework? So let's take a step back and see what we want to do, right? So we have some ideal functionality, and now we want to implement that ideal functionality with some hybrid protocol, like a protocol that uses other functionalities. And here, like the relation that we want to have in the zero knowledge protocol actually should talk about algorithms of all these other things. Right? So that's what we think we want. And that's how we would end up defining the relation, right? I think, and that's actually the mistake here. So if we would do that, then whenever we do such a hybrid protocol, we would have to prove that whatever these algorithms say, that has some relation, some behavior of the other functionality. So we would have to do all the proofs like one big proof all over again. So that's actually not what we want. It's a mistake here really is that we talk about this relation in terms of algorithms, but really if we use the UC protocol, what we want to do is talk about the relation, how different functionalities behave, right? So when we do a credential proof, I want to prove that I have maybe a commitment on a message from which we also know a signature. So I want to talk about how inputs to the signature functionality and the commitment functionalities behave with respect to each other. And this I can only do if actually the zero knowledge functionality talks to this other functionality. So zero knowledge would have to talk to the signature functionality. That, okay, here's a message I got and the signature I got from the prover. And you tell me whether this is valid or not. And if it's valid, then actually I'm going to produce a proof that the zero knowledge statement is valid. Or if it was interactive, then I'm going to tell the verifier that this is true. So that's actually how we would want to use a zero knowledge functionality in the real protocol construction. Unfortunately, that doesn't quite work in the UC framework because the UC framework would not allow you to do this. So we have to step out in the UC framework here a little bit. And the issue is namely that, sorry, let me take a step back. So then once we have that, of course, we want to implement that. So we want to have somehow proof that when we instantiate the different parts, that in that case, actually, the instantiation would work. Now you can see in this picture, actually, it's funny, right? So on the right-hand side, the zero knowledge protocol instantiation, of course, is about algorithms. It can be no other way. So actually, what we would have to do is find some kind of proof mechanism or composition framework that sort of removes the interaction of the zero knowledge functionality such that actually can be implemented by the zero knowledge protocols. There's really two issues here, right? The first one is that this thing here is not subroutine respective because now the protocol calls the functionality, it calls another functionality, but it also calls the functionality directly. So that's not subroutine respective. So the UC theorem actually does not apply. And then the second problem is really so that when you have the instantiation, this interaction does no longer exist. And actually, we do not want it to exist because otherwise it wouldn't work. So how can we address that? Well, let's look at that. I guess the first one here is the subroutine respective. This one actually you can just look at the UC theorem and make a more generic version of the theorem that deals with composition. If there was some interaction between this between different functionalities, so that works. So in there's a paper that Björn Takman and Drivers and myself have written last year, where we provide like a multi-protocol composition framework that sort of extends the UC framework to deal with these cases. So that we can deal with. The part here is harder, and actually let's focus on that. So I guess what I want to do now is I want to say, okay, so how can we prove that this and this are the same? So how can we do that? And so it's here, well, the first step is, I'm just looking at the non-interactive zero knowledge functionality here. So we want to, our goal is to prove that the protocol, that the instantiation actually realizes the functionality we had on the other slide. The first step is here, because over here we talk about the real protocol. Then we abstract it away in the non-interactive zero knowledge functionality with respect to relation. And actually, that first step, we can just do it because this is really the normal, the UC functionality that Groth and others had defined. We just define this relation here to be about these algorithms that we have implemented. So that's easy. That's standard UC framework. Now, the next thing that we do is instead of returning sort of the relation into a predicate that does no longer sort of, you know, like look at the bit representations of the algorithms, but just calls sort of, let's say, Turing machines that implement those algorithms. This is really just like a conceptual state here. So we're just rewriting the functionalities such that you don't call these algorithms, but sort of call the Turing machines. But it's really a mental step here. Now, in the next step, actually, what we can do is now we can say, well, good. So we can actually replace the algorithms here by call to the implementation. That again is just a conceptual step. But I mean, of course, the implementation of a signature scheme would also provide the signature, et cetera, et cetera. But it's not hard to see that actually this works as well. So it's another standard UC. Now, the part that comes next is that now we want to externalize these algorithms. So instead of calling these algorithms internally, we want to call them externally. We want to get to this statement here. And now, of course, we also have to allow other parties to use this protocol. So now in this step, actually, we need to have like a multi-protocol composition theorem. So it's really this step here because now we're also allowing other parties access to these Turing machines. Okay, good. So if we take this, you know, like now we have like a way how to prove that the algorithms here, the zero-knowledge implementation with the algorithm really realizes this party here. So we can replace that. So we can go back. Okay, so this is just another way to rewrite F because now actually this, what we have here, our this modification is really what we had on the other slides. It's the same thing, it's just renaming. And so as you can see now, I can actually go from this here on the left-hand side, the realization with all the different primitives. I can replace this one here. Well, the first step is I replace the proof instantiation with the ideal functionality that now actually talks to the different protocols, whereas here on the left-hand side, it did not talk to the protocols, but that we just proved is the same thing. Now, if I have that, then actually the composition theorem now also says that since fsig, the protocol sig here realizes fsig, I might as well replace that with fsig, and so I get this statement, right? And that's exactly what we wanted to have. So now, along those lines, I can actually prove that if I have a hybrid protocol that implements my credential functionality, then also I can instantiate that with primitives. So the summary here is that, well, actually the proof I was just showing on the different steps, that in fact we need to do for all the, for every predicate. So if I have a zero-knowledge proof that does talk to, I don't know, yet another primitive, or if I want to prove that I have a signature on a commitment scheme, which contains an encryption, which is again containing a signature. So then I have to do the proof steps I was just showing you before again. But on the other hand, all these proof steps are really generic. So you only need to do it once for that relation. But otherwise, whether you do that with one instantiation of a signature scheme or another instantiation, that doesn't matter. That doesn't depend on that. So really what we get is we want to do a protocol design. First, we define the overall functionality. Then we define the hybrid protocol and the relation here. Then we will prove that the hybrid protocol satisfies the overall functionality. And then we would apply the steps we just talked about to show that actually there is an instantiation of the zero-knowledge proof protocol that works. And then I was saying, so there's the details of this composition theorem and sort of the steps are in that paper here by Moderators and Björn Takman at myself. So I guess the conclusion. So there's like conclusion for the three parts. So the first one is that there's a number of frameworks about around zero-knowledge protocols that actually are very nice, that allow you to construct protocols, efficient protocols with zero-knowledge proofs. I guess for the post-quantum, there's like more work needed there, but otherwise there's a lot of practical protocols that we could do already. Because most people, when they do these proofs, they actually do them in a monolithic way, so or maybe they have a UC functionality where they make a statement about or like define a UC functionality, but then when they prove the realization implements that functionality, they have to go back and do like a very monolithic proof, so they cannot actually use the power of the UC framework. And so that was really like what the third part is about, so which I guess maybe in some sense is the most important message to me today, is really that we can actually do modular proofs in something like a UC framework. We just need like another theorem, like a composition theorem, but other than that, just replace the UC theorem by that new composition theorem, and they're all done, because it just deals with this the case that you would call sub-functionalities also from other functionalities, so that deal with the case that if a hybrid protocol is not subject respective. And then also there is now like a proof methodology how to do modular zero-knowledge proofs in this kind of framework. And so I guess overall, of course, there's still more work to be done, which is great, but I guess we are already sort of flying around in space, but there's more stuff we can do and need to become even better spacefarers. Thank you very much.
Thank you, Ian, for the great talk.
Thanks.
Yeah. So I guess I can start with some questions from the group chat channel. So Claire asked about the quantum security, especially for the authentication use cases, referring to the Schnorr schemes.
Yes, so for the Schnorr schemes, indeed, I think that they're, they are based in discrete locks, so they would not be quantum secure at all, right? As we all know that these discrete locks are breakable by quantum computers. So indeed, so we should either go to some lattice-based assumptions or to use, I guess, Starks with hash function-based primitives. So if you're worried about quantum security, then the Schnorr-based protocols and also the gross-to-high-based approach would not work.
And then Dario asked about, is this lack of generality of statements a drawback of the Schnorr schemes?
Yes, it is, right? But I think that's also what makes Schnorr schemes more efficient. So it's like this, I guess, balance between being very generic, because if you would use a generic zero-knowledge proof protocol, then typically it would not be efficient. I guess there's some, I mean, if you go for, it depends also on the, let's say, so if you have the, for instance, gross-to-high proofs, yes, the proofs could be short, but the work that the proofs and the verifier might have to do ahead of time and so on is not so efficient as it would be maybe for the prover in the Schnorr protocol. Because there's a lot of advantages in some of these things where, depending on the use case, actually it might be better off to maybe use bullet proofs instead of Schnorr proofs for some applications.
Mm-hmm. And then Markov asked, so on slide 32,
let me go back.
Also to go to, yeah.
Because I'm still sharing my 32.
Yes, you're still sharing. Yes.
Okay,
so yes. So does the first part of the proof involve only hybrid functionalities or also game-based definitions?
Well, in my view, it should only involve hybrid functionalities, right? I mean, but as I was saying, there's a lot of people actually do these steps. Let me maybe go a little bit more, here, that use like an ideal functionality here, then have a protocol, and then for this step, combining these, they use game-based or property-based definitions, right? But then you end up with sort of monolithic proof, and that's actually what I wanted to get away from. I really want to use the power of the composition theorem and the UC framework, because if you use the UC framework here, then actually the proofs that your hybrid protocol satisfies, this proof here should be way easier, right? And if you use property-based definition, so essentially what you do is you go from here to here in one step, right? You cannot do this intermediate step where you say, okay, my hybrid protocol actually satisfies this, because that would only be possible in the UC framework. Otherwise, you have to do like monolithic proofs. And then that's actually, those get very complex very quickly, because you probably have all seen proofs that are, if done correctly, 60 or more pages, and it's very hard to actually verify those. So that's, I think we actually need to use something like the UC framework and the hybrid protocols to actually use the full power, because only in that way we can get protocols that are easy, somewhat easy, at least easier to verify.
Thanks. So, and then finally, Dario asks, so I think it's referring to the second part. So, so having to prove completeness outside UC, is that really a problem? Because most security flaws are not due to completeness problems. I think it's referring to the part where you combine the functionality of signature and the functionality of zero-knowledge proof with the relation. So is the security problem of completeness, or both?
No, I guess, yeah. No, not sure what to answer, because at the end of the day, of course, you want to have everything inside the security framework, so you would not want to go outside. But then, of course, in reality, if you just could prove some properties in the security framework, maybe that's good enough for you as well. And also, if you look at some UC functionalities, actually, those tend to sometimes also, if you do them right, also get quite complex. Actually, might even want to do some, some analysis of a UC functionality and prove that it satisfies some properties that you're interested in. Right? I mean, if you see a functionality of a credential system, it will be quite complex, and then how would you be sure that it provides anonymity? Sometimes you could just look at it and say, wow, okay, there's nothing provided to the adversary that leaks stuff. But sometimes actually it's not straightforward at all, and you might have to do like a next level argument that actually your functionality really does what you think it does.
Okay. And do you have like follow-up questions or questions from the audience? You can just
I had a short question. So you define this new functionality for NISQs with three different primitives that they can interact with these functionalities. So is it the case that, for example, if we want to use signature in your new framework and prove that it achieves MUC, so we need to define something similar to your functionality for NISQ? For example, we should define a new functionality for signature which interacts with different, functionalities, and then we can prove that it can achieve MUC, or I got it incorrectly? This is misunderstood.
Well, like I said, there's two parts. So one part is that very often, if you look at functionalities in UC, so for instance, the signature scheme, just the way they're defined today is a little odd, because it doesn't allow for protocol composition really, which is, if you think about it, really odd, because you think about the UC frameworks. Okay, you want to do composition, you define, and then you think, okay, so now I'm giving a functionality for a signature scheme or for a commitment scheme in UC, but then the way it's done now, actually doesn't allow you to compose things, right? Somehow, I think, although it has composability in the title, it doesn't really compose, because it doesn't work if you compose, right? But I think that those are, like for signature scheme, you just make the parameterize the functionality with the signatures, and it's fine. So very often it's not very difficult to change it. Or for encryption scheme, same thing. You just change the also parameterize it there, and it would just be fine. For commitment scheme, the typical commitment functionality is interactive as well. So that wouldn't work either because you really want to have a commitment out there. But also there you can make a non-interactive version of commitment scheme that just works fine. So it's more like when people define those functionalities, they don't have protocol composition in mind, right? I think that can be dealt with. Now, the other thing, because my other point is that when we think about zero-knowledge functionality, actually, what we really think about is a functionality that talks to this other functionality, because when I design a protocol, it's like, here's proof that this is a signature, this is a commitment, and this is a message. And that actually is, those should really be a statement when you design a hybrid protocol that talks about the input to this other functionalities and not about algorithms, right? You want to talk about the functionality and not about the algorithms. So that's why actually you need to have this interaction here. And of course, in the realization, on the other hand, it's different. There you don't want to talk about the algorithms because that's how you can only implement them. So that's like somehow like a gap, but I don't know. I mean, that's actually in some sense not bad because we can deal with the gap. It's not hard to deal with it. It's just, I think if you think about how to do it more naturally, I think that's the right way to think about it. Does that answer the question?
Yes, thanks.
Cool.
I think we are running out of time. So if you have maybe actual questions, maybe we can take it offline, and let's thank Ian again for the talk.
Thank you. My pleasure.
There were a couple more questions in the chat, I think. About the CRS model.
Do we need
it was
to,
really fast. In the functionality that you're defining is in the CRS model, the random oracle model. Like, do you have a functionality CRS? Do you have functionality random oracle, or works on both?
Well, I guess this is like generic, so it would work for anything. But yeah, if you want to talk to the random oracle, then of course you need to define your functionalities also in the random oracle model. Actually, because there's like 2 or 3 papers that talk about the random oracle model in the UC framework. Because I've done one maybe 3 years ago on how that would work. Because Alessandro and Canetti have done one with a bit more limited scope, so ours is an extension of that. So you would have to deal with that. And CRS is yet another kind of worms that would probably merit a few papers as well.
Yeah, great, thank you. So I think we are going to have a networking session next, right? Daniel and Yao.
Yes. So today we're gonna have a really special network